Good morning, good evening, good afternoon, and welcome back to another math lesson. Today we're going to do part 2 of analyzing rational functions, okay? Specifically looking at now what rational functions are and how to define them, and then go ahead and graph them, okay? So let's go ahead. Let's get started. A rational function is a function in the form of f of x is equal to p of x over q of x, where p of x and q of x are polynomials, and q of x is not equal to 0. So let's go ahead and let's highlight that because that's kind of important for us to know. Okay, and q of x are polynomials where that's not equal to 0. So examples of rational functions are f of x is equal to 2x plus 1 over x squared minus 4. Okay, g of x, so this is just another example of another function, is x to the power of 3 plus 6x divided by x. And finally, h of x, so another function, x minus 1 divided by 2. Okay, so what we're going to do now is we are going to go through the characteristics of rational functions, okay, and then give examples on how to graph them, okay? So step number 1 is non-permissible values of x. So how non-permissible values, I like to also call them NPVs. So if you hear me reference and say NPVs, I'm talking about non-permissible values of x, okay? So those create vertical asymptotes. So that again is a vertical line that approaches but never touches. Okay, so it is drawn as a dotted line. Okay, I explained that in the part 1 of the lesson, okay, what a vertical asymptote is, but here is the example of it. Okay, how to find it? Very important. To find a vertical asymptote, you set the denominator equal to 0 and solve. Note, and this is very important, this may require you to factor. Okay, so if we were to look at the first example, okay, we have y is equal to 1 over x minus 3 multiplied by x plus 1. So we need to figure out where exactly these particular vertical asymptotes are. So we need to figure out where the NPVs are. Okay, so let's go ahead, let's get started. So if we have, that means x minus 3, x plus 1 is equal to 0. We want to set them to 0 to find them. Okay, so we have x minus 3, x plus 1 is equal to 0, which means that x minus 3 is equal to 0, and x plus 1 is also equal to 0. That means we have a vertical asymptote at x is equal to 3, and a vertical asymptote at x is equal to negative 1. So we can go ahead and graph them. So at x is equal to 3, 1, 2, 3. Remember, as a dotted or dashed line. Draw arrows at the end to signify that the asymptotes do continue. Okay, and then draw another one on this side. So all we're doing in these particular examples is we're just drawing out the non-permissible values. Okay, stating that this is x is equal to 3 and x is equal to negative 1. Very similar to what I showed you in part 1. Okay, so there you go. For the next example, we have x is equal, or y is equal to x plus 4 divided by x multiplied by x plus 3. So again, we set the denominator to 0, and in this case, we've already factored. Okay, so we don't need to factor anymore. So this is now x, and then x plus 3 is equal to 0. That means that either x is equal to 0 or, okay, x plus 3 is equal to 0, which means that x, another non-permissible value is going to be at x is equal to negative 3. So those are our vertical asymptotes for this particular example. They will be at x is equal to 0 and x is equal to negative 3. Okay, so let's go ahead and let's draw those out. So x is equal to 0, like so. And then negative 1, negative 2, negative 3. Let's draw those out here as well. Arrows at the end. And we are done this example. Okay, moving on to the next characteristic of a rational function. We have points of discontinuity, or again, as I like to call them, or if you hear me call them, POD, or pods, okay? A point of discontinuity, or a POD, or a pod, is basically a hole in the graph, okay? It is drawn as an open circle, okay? So it's essentially a spot where it does not exist, okay? So to find the point of discontinuity, so remember a coordinate point must have an x and a y value. We are to determine the x factor of we are to determine the x value of the factor that is common in both the numerator and denominator, and solve the remaining function using substitution to solve for the corresponding y value. Essentially what's going to happen, okay, you factor. If something were to cancel in the factoring, that is now a point of discontinuity. And a point of discontinuity, remember, we need to state the x and y coordinate. It's a coordinate, you have to state both. Okay, for a vertical asymptote, it's just x. For a horizontal asymptote, it's just y. Okay, but a POD, you need to state both x and y. Two things. Okay, let's try this example. Okay, we have y is equal to x squared minus 5x plus 6 divided by x plus 3. Or sorry, x minus 3. Right away, we need to determine what our non-permissible values are. Okay, so the NPV, so whatever number that sets our denominator to 0, okay, that's what the NPV is. Okay, so this particular NPV is going to be at x is equal to 3. Okay, so that's where our NPV is. What we need to do now is we need to factor the numerator and see if anything cancels. If something cancels, we have a point of discontinuity. If nothing cancels, we have a vertical asymptote at x is equal to 3. Okay, so let's see if something cancels. So x squared minus 5x plus 6. So this factors to x minus 3 and then x plus 2. And this is being divided by x minus 3. Okay, so from this we can see that the x minus 3's will cancel. Okay, so now because the x minus 3's cancel, we are now going to use this new form, y is equal to x plus 2, as a way to determine what the point of discontinuity is. Okay, so we are going to set, okay, so let's let x is equal to 3. Okay, so that means we're going to have y is equal to 3 plus 2. So y is equal to 5. That means, okay, in this case, we have a point of discontinuity at the point 2. Oh, no, sorry, x is 3 and y is 5. So at this particular point, 3 and 5, that is where our point of discontinuity is. If nothing canceled, okay, then we have a vertical asymptote at x is equal to 3. But since the x minus 3 is canceled in our when we factored, that becomes now a point of discontinuity. You need to state both x and y. So now what we're going to do is we're going to graph this particular function. So it's a linear function of x plus 2, but at 3 and 5, it'll be a hole in the graph. Okay, so it's going to look something like this. So at x plus 2, that means we'll have a y-intercept of 2. Okay, so this is going to be 1 and 3, 4 and 2. 3 and 5 is going to be a hole in the graph. Open circle. Everything else will remain the same. And everything past will remain the same. So how this works is you will draw your regular linear graph, okay, up to that point. Don't go through the point, okay? Because that's a hole in the graph. It doesn't exist at that point. Okay, and then you just pick up where you left off right after the point. Okay. Okay, and that is how you would draw this particular graph with a point of discontinuity. Okay, let's try the next example. So the next one is y is equal to x squared minus 25 divided by x plus 5. So right away, we can determine that the NPV, okay, your non-permissible value is that x is equal to -5. That'll set the denominator to 0. That'll make that undefined. Okay, so we have an NPV at x is equal to -5. Let's factor to see if anything cancels. So x squared minus 25, so that's y is equal to x minus 5, x plus 5, all being divided by x plus 5. Well, in this particular case, the x plus 5's cancel. And all we have left is y is equal to x minus 5. What we are going to do, because those have canceled, we are now going to find the POD. So we're going to say let x equal -5, because that was the NPV from before. So we're just going to use that NPV now to find the point of discontinuity in our new function. So y is equal to, this is going to be -5 minus 5. Okay, So now that's going to be y is equal to negative 10. So the POD is going to be at with x is equal to negative 5 and y is equal to negative 10. So to put them together is negative 5 and negative 10. Okay, just like that. So now we can go ahead and graph it. Okay, it's going to be a regular linear graph again, starting at the y-intercept of negative 5. So 1, 2, 3, 4, 5. And then you're just going to keep going down. Okay, so 6, 7, 8, 9. Well, I actually ran out of room, so it's going to be down here somewhere. So that's our point of discontinuity there. At x is equal to negative 5 and y is equal to negative 10. So again, you're going to draw your graph through that point of the y-intercept, okay, but not through the point of discontinuity. That's a hole in the graph. It does not exist there. Okay, so I would say 1, find your NPVs. Find NPVs. 2, factor. 3, okay, cancel if you can, obviously. So I'll say if you can. Okay, so this is 4. If an NPV canceled, right, gets canceled, it becomes a POD. Okay, if it doesn't, so if an NPV does not get canceled, okay, it becomes a vertical asymptote. A vertical asymptote. So there you go. That's one thing we need to remember, okay? So if an NPV gets canceled, that number now becomes a point of discontinuity. If it doesn't get canceled, then it becomes a vertical asymptote. Moving on to example number 6. It says determine any non-permissible values. Okay, so right away with this particular example, y is equal to x squared divided by x squared minus 9. What we need to do is we need to factor. Okay, right now we can't determine what the NPVs are. I mean, if you can, wonderful. If you can't, factor first, and then we can determine them. So if we factor, this now becomes y is equal to x squared over x plus 3, x minus 3, okay? Because this is a difference of squares, okay? So we can now determine that there are NPVs. Okay? NPVs at x is equal to positive and negative 3. That's where the NPVs are. Okay, so if we go back up for a moment, if an NPV gets canceled, it's a POD. If it doesn't, it's a vertical asymptote. An NPV does not get canceled. So that means that both of these, okay, they will be vertical asymptotes. So that means we have vertical asymptotes at x is equal to positive and negative 3. Okay, so that's part of the example there. Example B, y is equal to x squared minus x minus 2 divided by x plus 1. We can figure out what the NPV is right away. So an NPV is at x is equal to negative 1. What we need to do now is we need to factor the numerator to see if anything cancels. So this factors to x plus 1, x minus 2, all being divided by x plus 1. So in this particular case, your x plus 1's cancel, and we have y is equal to x minus 2, which means now we have a POD because an NPV was canceled. Okay, so now let's let x is equal to negative 1. So it's going to be y is equal to negative 1 minus 2. So that means y is equal to negative 3. So that means we have a point of discontinuity at, again, x is equal to negative 1. Y is equal to negative 3. Put them together as a point because they need to be stated as a point. So it's negative 1, negative 3. This needs to be stated. Okay? Make sure you state them as an ordered pair as a coordinate point. Okay, so this is how you would get full marks. Okay, so don't forget that. Okay, last characteristic we'll go over, horizontal asymptotes. Okay, so for when y is your p of x over q of x, so your rational function where p of x and q of x have no common factors, the following occurs. If the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is the line y equals 0. Okay, so again, the degree is the power. Okay, so if the power is higher in the denominator than it is in the numerator, you have your horizontal asymptote will be at y is equal to 0. So again, this, for example, okay, so this particular example of y equals 1 over x is x to the power of 0 divided by x to the power of 1. The power in the numerator, or so the power in the denominator is greater than the power in the numerator. Okay, so that means that this is y is equal to 0. Okay. The next one, okay, so this one is, again, the greatest power in the numerator is x to the power of 1, and the greatest power in the denominator is x to the power of 2. So again, the power in the numerator is less than the power in the denominator. Okay, and the last one, we have, again, x to the power of 0 over x to the power of 1. So because of this, we have a horizontal asymptote at y is equal to 0. Because the degree in the numerator is less than the degree in the denominator. So you just need to look for those for the highest power and use those numbers, okay? So that's the first set. Okay? The second, if the degree of the numerator is equal to the degree of the denominator, the horizontal asymptote is at the line y equals a over b, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. Okay? So if the degrees are the same, okay? So if the degrees of the numerator and denominator are the same, okay, right? You will get a horizontal asymptote at a over b. A is the leading coefficient of the numerator, b is the leading coefficient of the denominator. For example, y is equal to 2x squared minus 1 divided by 3x squared plus 5. Because there are two x squareds in the numerator and denominator, all we're going to take is the 2 over 3. So this is going to be y is equal to 2 over 3. Okay? Let's rewrite that further down. So this is going to be a horizontal asymptote at y is equal to 2 over 3. We just want the coefficients out in front. So the numbers in front of the x, the highest power, the highest degree. Okay? So the next one, y is equal to 2x squared plus 2 divided by 4x squared minus 1. So again, because there are x squareds in both the numerator and denominator, same degrees, you're just going to take the coefficients, so the numbers in front of the x squareds. So you have a horizontal asymptote at y is equal to 2 over 4, which is a half. You can simplify it. And finally, the last one, we have y is equal to 2 minus x over 1 minus x. Well, again, it's x over x, but remember, this negative affects the coefficient in front. So it's going to be a horizontal asymptote at y is equal to negative 1 over 1, which is negative 1. Okay? So again, if the degrees are the same, just look at the coefficients in front. Okay? That, for your numerator and denominator, that will be where your new horizontal asymptote will be. Last one, if the degree of the numerator is greater than the degree of the denominator, then there will be no horizontal asymptote. Okay, so this would generate an oblique asymptote. So what do I mean by an oblique asymptote? Well, that's basically a y equals mx plus b asymptote. Okay, so in this particular example, y equals x to the power of 3 divided by x squared plus 3. Again, there's no horizontal asymptote. Okay. It basically would create an oblique one. So we would create an asymptote as a y equals mx plus b. Okay? So that is how the different ways to figure out your horizontal asymptote. Okay? So for this course, we're not going to look at oblique asymptotes. We're just talking about horizontal asymptotes. Okay? So for the sake of this course, okay, y equals if the degree of the numerator is greater than the degree of the denominator, there are no horizontal asymptotes. Okay? let's go ahead and let's do the next bit of examples to kind of hone our skills. Okay. Determine the equations of all the asymptotes and the coordinates of any points of discontinuity. Okay, so let's go ahead and let's try this out. Okay, 7a. Y equals 2x divided by x squared minus 4. Okay. I myself, how I teach is I actually do the horizontal asymptotes first. They are the easiest ones. No factoring required. You just look at the degree in the numerator and denominator. Okay. So since we have an x divided by an x squared, so we have the degree is greater in the denominator than the numerator, we have a horizontal asymptote, okay, at 0. Okay, y equals 0, okay? Now we can look for our NPVs, vertical asymptotes, and points of discontinuity if there's any. So what we need to do first is we actually need to factor this y is equal to 2x over x squared minus 4. So this is y is equal to 2x divided by x plus 2, x minus 2. Again, it's a difference of squares, so that's what the factoring becomes. Because nothing cancels, before we get to that, we have NPVs at x is equal to positive or negative 2. Because nothing cancels, we have vertical asymptotes at x is equal to positive or negative 2. So I personally like to do horizontal asymptotes first because there's no factoring required. You're just looking at the function itself and determining which degrees are higher, numerator and denominator, and then determining the horizontal asymptote from that. And then you get into factoring and determining the vertical asymptotes in PVs or points of discontinuity. Okay. Let's try the next one. B. B says y is equal to x squared plus 2x divided by x squared minus 4. So in this case, because there's an x squared in the numerator and denominator, okay, we have our horizontal asymptote will change. So our horizontal asymptote will be at y is equal to, well, the coefficient of the numerator is 1 and the coefficient of the denominator is also 1. So it's going to be at y is equal to 1. Okay. Next up, let's factor. So y is equal to, this is x, and then x plus 2 divided by x minus 2, x plus 2. Before we do any canceling, the non-permissible values are at x is equal to positive or negative 2. Okay. All right. Now we can cancel. The x plus 2's cancel. Okay. That means that we have a vertical asymptote at x is equal to, well, it's this example here. Okay. So this is going to be at a vertical asymptote at x is equal to 2. Okay. That's one of the NPVs. We need to figure out the coordinate of the point of discontinuity for the other NPV. So that means we have a new equation of y is equal to x over x minus 2. So now what we're going to do is we are going to say let x equal negative 2. The other NPV that wasn't used. Okay. So it's going to be y is equal to negative 2 divided by negative 2 minus 2. So that's y is equal to, well, negative 2, what's negative 2 minus 2? So it's negative 2 over negative 4, which is equal to 1/2. So the point of discontinuity is at negative 2 1/2. Moving on to the last two examples. Okay, we have y is equal to x plus 1 divided by x squared minus, or plus x minus 2. So again, first thing to find is our horizontal asymptote. Since we have an x to the power of 1 in the numerator and x to the power of 2 in the denominator, we have a horizontal asymptote at y is equal to 0. Okay. Okay, so now we can factor this. This is going to be y is equal to x plus 1. Okay. In this particular case, it looks like we have factors that x minus 1, x plus 2. Okay. Nothing seems to cancel at this point, so we have our NPVs are at x is equal to negative 2 and 1. And since nothing cancels, we have vertical asymptotes at those particular points. Okay, x is equal to -2 and 1. Okay, there are no points of discontinuity in this because nothing cancels. Okay, so because nothing cancels, we have vertical asymptotes. And finally, moving on to the last example, we have f of x is equal to x squared minus 3x plus 2, all being divided by 1 minus x squared. So again, before we start, we can determine our horizontal asymptote. Okay. We can determine that because there's an x squared in the numerator and denominator. So it's going to be y is equal to, well, the coefficient for x squared is 1, and the coefficient for the other x squared is -1. So it's going to be at 1 over -1, which is -1. So what we'll do now is we will factor. So we have f of x is equal to, if we factor out the negative in the denominator, we can actually factor it out a little bit better. So we have x plus 1, x plus 2, and the numerator all being divided by negative. Okay, and then x plus 1, x minus 1. So what I did is I factored out the negative so that it would switch the signs. So this negative, the 1 minus x squared, would become negative x squared minus 1. So I just factored out a negative so it would switch the signs, which makes it easier for us to cancel. Okay, so we can now, okay, so that's what this becomes. All right, we can now cancel, or sorry, before we get to canceling, I'm getting ahead of myself here. Before we cancel, we say the NPVs are at x is equal to positive or -1. Okay, now we can cancel the x plus 1s. So we have f of x is equal to, we have negative x plus 2 divided by x minus 1. It doesn't matter where the negative goes, right? So now that I factor out a negative, it can be in the numerator or denominator, it does not matter. We can also say that we have a vertical asymptote now, and that's at the one that's left, x is equal to 1. We need to find now the point of discontinuity. So we're going to let x is equal to -1, and now we will determine, okay, what it will be. So that means we have f of -1 is equal to negative multiplied by -1 plus 2. So just substitute in -1 everywhere you see x. -1 minus 1. Okay, so that's going to be equal to -1 plus 2 is positive 1. Multiplied by -1, so that's -1. And the numerator divided by -1 minus 1, that's -2. So this is equal to 1/2. So the point of discontinuity is at x is equal to -1 and 1/2. Okay. Make sure you state it as an ordered pair. Okay, make sure you state it as a coordinate. Okay, so your point of discontinuity is at, and make sure you put it in brackets, -1 and 1/2. Well, that is it for today's lesson on analyzing rational functions. I hope you enjoyed it. Remember, when it always comes to math, keep calm and show your work.